Hello everyone, this is Vinay. I am a senior graduate student at the Institute of Mathematical Sciences, Chennai. It gives me great pleasure to discuss our recent work which is about studying the rheological response of a binary colloidal glass where the size ratio is a bit large. This work has been done with my PhD advisor Pinaki Chaudhary and our collaborator Yukan Horbach at University of Dusseldorf. To see this work in detail, please refer these two archives. In our daily life, we see a variety of materials having various applications in industry and nature where the size of the particles ranges from a very small value to large value. The microscopic understanding of dynamics and rheology is important in developing applications and also to design various new materials. There have been a couple of works in this direction, and this is one of the early work by Imhoff and Daunt, where they have used experimental techniques to construct a phase diagram using hard spheres. Here they show for the small presence of packing fraction of the smaller particles with the bigger particles, there exists a phase of fluid of smaller particles and crystals of bigger particles. With the increase in the packing fraction of smaller particles, there exists a glassy phase of bigger particles with the fluid phase of smaller particles. With the further increase in the packing fraction of a smaller species, there coexist glassy phase of bigger species with the glassy phase of smaller species. Our regime of interest is this, where there coexist a glassy phase of bigger species with the fluid phase of smaller species. There have been a couple of recent works also. This is one of the recent work where people have tried to understand the structure, microscopic structural changes happening in the system with the inclusion of smaller particles, where they report softening of the material with the small number of inclusion of smaller particles and latter hardening of the material with the large number of inclusion of smaller particles. In particular, I would like to mention these two works where people report huge separation in relaxation time scales of bigger and smaller species. As we can see here, the diffusivity of the system of a bigger and a smaller species as plotted as a function of density, and we see the diffusivity of bigger species vanishes above a critical density, but a small particle diffusivity is finite even at higher density, and this shows anomalous dynamics. The physical picture appearing here is like this, where the smaller particles are moving in the glassy frozen matrix of bigger species. There have been only a few studies that we know where shear response of such mixtures have been studied. Here, this is very interesting to see how the external time scale introduced by shear competes with the widely separated time scales of bigger and smaller species present in the system. Our goal here is to develop microscopic understanding of the macroscopic observations. The model that we use is the same model which has been used by Voigtman and Horbach in earlier paper that I mentioned in previous slides. In this model, particles are interacting via soft repulsive potential. This is a 50-50 mixture where the bigger A particles are shown in green and the smaller B particles are shown in dark blue. The mean size ratio between bigger and smaller particles is close to 2.85. As we can see here, bigger particles mostly occupy the volume, and the cross interaction between bigger and smaller particles is very small. Also, the temperature of the system is maintained at to a fixed value. We do molecular dynamic simulation of such system by varying the density from a very small value to large value. At first, we study interdiffusive processes happening in the context of such binary mixture where the size ratio is a bit large. Interdiffusion is related with the intermixing of the two species present in the system. In order to measure this, we track the center of mass motion of the bigger species, which can be used to measure the interdiffusion coefficient DAB by measuring the mean square displacement of the center of mass. And further, the interdiffusion coefficient DAB can be expressed in terms of diffusivity of the center of mass. Here we measure the mean square displacement of the center of mass using bigger species, and uh, we also report single particle mean square displacement of bigger species, single particle mean square displacement of smaller species. Using these measurements, we can estimate corresponding diffusivities, which is DSEM and dA and dB, which have been plotted here as a function of density. And we can see here bigger particle diffusivity dA initially decreases and then follows the diffusivity of the center of mass, and also show finite value at even very high densities, and the smaller particle diffusivity is followed by the interdiffusion coefficient. All these measurements at higher density show that system is showing finite diffusion in terms of bigger particles, which is not expected because at these densities bigger particles are forming glass. This is happening because the center of mass motion of bigger and smaller particles are interlinked. Since smaller particles are fast, their center of motion is moving, and as a result, bigger particle center of motion is also moving, which is causing this presence of this unphysical picture. In order to rectify this, what we suggest that this single particle measurement should be done in their respective center of mass. As we can see here, the measurements in these dotted lines are measurements done in the frame of their center of mass. And we can see here that at very high densities there exists a prolonged plateau which is expected for mixtures which are showing glassy dynamics. So, keeping this rectification that we suggest here in mind, now we want to understand the shear response of the system in the presence of various shear rates. So, what we do, we apply shear at different shear rates and we see yielding of the material and then reach in the steady state. So, we do measurements in the steady state, and again I would like to point out that it would be very interesting to see here how this time scale introduced by shear competes with the internal relaxation time scale of the which are widely separated of the bigger and the smaller species. Our control parameter here is the shear rate that we apply and the density of the system that will vary from a very small value to large value. At first, we report these macroscopic observations where we measure a steady state stress value of the system as a function of shear rate. So as we can see here, at very small density, the stress is proportional to the shear rate, which is Newtonian, which is the Newtonian behavior. But with the increase in the density, we start seeing appearance of curvature, which is a signature of non-Newtonian behavior. If we go to very high density, we see that at vanishing shear rates, this stress value becomes finite, which is actually emergence of yield stress close, and this happens close to a density mean mode coupling density of the system. And if we see the viscosity at very small densities, the viscosity is Newtonian. With the increase in the density, the system shows shear thinning, which is the decrease in the viscosity as a function of shear rate. In order to estimate the finite yield stress at vanishing shear rates, we use Herschel-Buckley form of rheology to estimate sigma naught, which has been plotted as a function of density above the mode coupling density. In order to understand the macroscopic picture of the system, we measure mean square displacement of bigger species and smaller species in the presence of shear at different rates and in the absence of shear with the dotted line. And we can see at a very small density where both bigger and smaller particles are moving fast, shear is not affecting their motion. But with a slight increase in the density, we see that bigger particles have slowed down and their motion is being affected by the shear, and a smaller particle motion is still not affected by the shear. At very high density, both bigger and smaller particles become slow and start responding to the shear. So we see here a density dependent response from the particles of the system. Now if we put the macroscopic and microscopic observations together, then here we on the macro part we put stress and viscosity as a function of shear rate, and here in the presence of shear, the diffusivity of the system as a function of shear rate of bigger and smaller particles. So we see here at very small density where there is Newtonian regime, at these densities, the diffusivity of bigger and smaller species is not depending on the shear rate. But in the intermediate densities where system is showing non-Newtonian regime, here the shear diffusivity of the bigger particles depends on the shear rate, but diffusivity of a smaller particle is independent of the shear rate. If we go to a very high density where we see the emergence of finite yield stress, so here we see that diffusivity of bigger particle shows power law type of behavior, and diffusivity of a smaller particle varies with the shear rate but not showing power law. Rather, it seems that it will show some finite value at vanishing shear rate. In order to understand the role of smaller particles, we also vary the composition of the mixture uh, with 100-0 composition where there is no a small particle, and then 75-25 composition, and then 50-50 composition. And we see here that at a different density, if we vary the composition, system becomes fast with the inclusion of smaller particles. And if we see the shear response, then we see the viscosity is lowered with the inclusion of smaller particles. So these observations are consistent with many earlier observations done in the system colloidal and granular systems. So just to conclude, we have studied a mixture where the size ratio is a bit large. We have studied the interdiffusion process in such mixtures, and we have done macroscopic and microscopic shear response of the system, and also established the connection between these two measurements. And we have varied the composition of the mixture to understand the role of smaller particles. To see these results in detail, please refer these two archived papers. Thanks for your kind attention.